Our JSON can nest any list inside any other list. That is syntactic closure, but it does not guarantee semantic composition. Group by consumes transaction rows and produces groups. Sort descending expects aggregate rows. Put sort directly after group by, and the connector refuses to close. Groups are not rows, and the grouped records do not yet have a total field. Insert sum. Its input is exactly the groups that group by produces. Its output is aggregate rows, exactly what sort requires. Sum is not a magical cast that hides a disagreement. It is the domain operation that actually changes grouped transactions into totals. Composition is valid because every adjacent output shape now equals the next input shape. The same flow can remain ordinary Python. Filter produces transaction rows. Group by consumes those rows and produces customer groups. Sum groups produces aggregate rows. Sorted consumes those rows. And an iterator slice keeps 3. The intermediate variables are not noise. They name the wires and make each boundary inspectable. Fix the configuration of each stage, and the whole pipeline has the familiar shape of function composition. The output of one function becomes the input of the next. Written with the composition symbol, reading runs from right to left. Drawn as data flow, it runs from left to right. The notation is secondary. The invariant is that the middle shape agrees. The Unix shell gives composition a compact surface. Cat emits the file. JQ filters and aggregates the JSON lines into tab-separated totals. Sort orders those totals numerically, and head keeps 3. The vertical bar asks the shell to connect each standard output to the next standard input. Under the command text is a graph of concurrent processes. Bytes can move from cat to JQ, while JQ is already writing to sort, and sort is already feeding head. At the operating system boundary, these ports all have the same broad shape. Byte stream. That mechanical agreement makes recombination easy. The JSON lines and tab-separated formats are additional protocols that the kernel does not type check for us. A process has more observable structure than one input arrow and one output arrow. JQ can send data through standard output, diagnostics through standard error, and an exit status back to its parent. It can also read files, inspect the environment, and cause effects. A parse failure may produce no pipeline data, one diagnostic record, and status 4. Ordinary function arrows hide too much of this contract. Concurrency adds time. Here the producer offers 5 records per tick, the consumer accepts 2, and the pipe holds 6. After the first tick, 3 records remain buffered. Then the producer begins blocking. 2 writes, then 3, then 3. The pipe is not merely passing a completed value. It is a bounded coordination mechanism, and a slow consumer can govern the speed of everything upstream. The clean algebra remains useful. A piece from A to B composes with a piece from B to C, producing a piece from A to C. Query operators and ordinary Python functions fit directly once their ports are explicit. Processes need a richer object with data channels, control, failure, effects, and time. Good abstraction does not erase those differences. It tells us exactly which structure is shared and which structure must be preserved. We can now design composition instead of hoping that nesting works. The recurring move is the same. Expose the hidden boundary, name its shape, and make the legal connection reusable. Our programs are already data that Python can inspect. Next, we ask a sharper question. Can the language itself construct code, control when that code is interpreted, and do so without accidentally capturing the wrong names?